Hello and welcome to my Physics 2211 Lab number 3 presentation about a black hole by myself, Zakir Ahmedin. So to introduce you to the main goals for the lab, one is using the net forces on a star orbiting a black hole, determine the mass of the black hole. The second goal is using the calculated mass from the black hole, known values of the mass of a spaceship and a planet, determine an initial velocity for the spaceship to pass close by the black hole. So we have some assumptions for this lab. One is that the net force on the star in part one is solely due to the black hole. Another is that the star's trajectory is determined based on our GT email. And the last one is that the black hole is going to be fixed at the origin. So we have several relevant formulae for part one. The main one being that the net force is equal to the force in the parallel and perpendicular directions summed together. So I also have it broken down by the force being equal to the the rate of the change in momentum. So we have the parallel and perpendicular components of that. And another key concept is going to be momentum, which is going to be equal to mass times velocity. That's how we're going to determine momentum to use these formulas you see at the bottom to calculate these forces. And then finally, we're going to calculate the second mass by rearranging the gravitation formula. Once we find the force, we can isolate m2 in this equation and then solve for it. So I can show you my glow script code for part one. So we have some gravitational constants, some masses, lots of basic assumptions that we're going to need to make. So here we have the initial velocity, or the initial momentum. It's going to be the mass times the velocity, as I've shown before, and we can find the delta v by subtracting the final velocity from the initial velocity. And then we can, this is the most important step right here, we're going to set the net force equal to dp dt. And then once we have this F net, we can find the mass of the black hole using this formula right here, which is the rearranged formula that I was talking about earlier. And then to find the mass of the black hole, we need to take an arithmetic average. So I counted how many times this loop ran, and then divided by that many times to find the average mass. So I can run the code. Just to save time, I can just show some final results. So we have the F net is equal to 7.0712 e to the 28th, and that the mass of the black hole is 9.9736 e to the 33rd. So what does it mean? So the question is, what is the difference between the net force and the rate of change of momentum? So essentially, these are the same thing, but they are calculated differently. dp dt, you only need to calculate the mass and the velocity, but for net force, you need the mass of the other object as well that's causing the gravitation, not only the mass of the object exerting gravitation. So we have a relevant formulae for part two. So it's going to be everything in part one, but then we're going to add the velocity update formula and the position update formula. So I can show you this computational model as well. Here we have the mass calculated in the previous part, and then some more constants. So here I kind of just guessed and checked these values. I just put in random values until I got a value to be able to enter the orbit, to exit the planet's orbit and not fall into the black hole. And here we essentially have the gravitation formula. And we repeated this several times to calculate all the forces on the object. For first, we have the net forces on the planet, and then we have the net force on the spaceship. And then here we have the Newton's second law update part of this, where we update the ship and the planet's position. So I can run this program as well. We can see that it gets close to the black hole, but then it exits, and it is not sucked in. So the what if question: what if you wanted to orbit the black hole instead of getting close to it? Well, the main thing is that you would need to have a lesser initial velocity. Because one way you could do this is having the spaceship stay within the planet's field of gravitation, such as our moon or objects that revolve in the ISS, for example. So if the spaceship orbits the planet, then it will orbit the black hole as well. So the current initial velocity has the spaceship quickly escape the planet and even the black hole's field of gravitation. So we could fix this by having it not leave quite as quickly and have a lower initial velocity. Thank you for listening.